Okay, in this video we are going to count the number of labeled trees on n vertices. Okay, so we are going to count the number of labeled trees on n vertices. Okay, so let's look at an example. Let's consider trees on 3 vertices. Okay, and here we can see that there is only one unlabeled tree on 3 vertices. So in that case the tree will look something like this. Okay, a path P3. Okay, so let's go and assign label to these vertices. Okay, one possible way to label the vertices is as follows. So we could label this by 1, this by 2, this by 3. Okay, another way of labeling the vertices is as follows. So we could label this 1 by 1 and this by 2 and this by 3. Okay, that is another possibility, and another possibility is something like, so we could label okay this by 3 and this by 1 and this by 2. Okay, and so I think okay, let's consider say one more. So if you go and label something like say 2 here, 3, 1, 3 here and 1 here. Okay, we can see that these two trees are exactly the same, right? Okay, so no need to consider the other two. So that says, okay, if you consider the labeled trees, okay, here we have okay 3 labeled trees on 3 vertices, and those 3 trees are this one, and this one. Okay, so okay, even though on labeling these 3 trees look different, they are isomorphic to each other. You can see that okay, this one is isomorphic to this and this one is isomorphic to this. Okay, but when we assign labels to the vertices, okay, we can have these 3 labeled trees. Okay, so for n equal to 3 there are 3 labeled trees. Okay, and let's see one more example. So for n equal to 4, okay, these are all the labeled trees. Okay, so here we can see that there are 16 labeled trees on 4 vertices. And if you look into the first row, here we can see that okay, these 4 trees are isomorphic, and all the remaining 12 are isomorphic to each other. Okay, and that says there are only 2 unlabeled trees on 4 vertices, and they are these 2 trees. Okay, one corresponds to this path P4. Okay, so here if you look into these 12, you can see that okay, these 12 are isomorphic to this P4. Okay, so this labeling that makes these 12 trees different. Okay, and similarly, okay, one isomorphic to this one, right? It will look something like okay. So we can see that there are only 2 unlabeled trees on 4 vertices, whereas if you look into the labeled trees on 4 vertices, there are 60. Okay, so let's go on to a general statement called Cayley theorem. So Cayley theorem says there are n to the n minus 2 label trees with n vertices for n greater than or equal to 2. Okay, so let's go and verify whether that is true here. So Cayley's theorem says for n we have n to the n minus 2. So here for n equal to 3 we have say 3 minus 2, okay, which is equal to 3, and those trees are these 3. And similarly for n equal to 4 we have 4 to the 4 minus 2, which is equal to 4 square, which is 16, and these are the 16 labeled trees on 4 vertices. So it seems like the Cayley's theorem is true for all labeled trees with n vertices. So statement reads as follows: there are n to the n minus 2 labeled trees with n vertices where n greater than or equal to 2. Okay, so before proving this theorem, okay, let me give a basic idea how to prove, okay, this theorem. Okay, so the basic proof idea. And here the idea is something like this. So we are going to establish a one-to-one correspondence between a labeled tree T on n vertices. So we are going to establish a one-to-one correspondence okay, so one-to-one corresponds between a labeled tree on n vertices to a sequence S on n elements of length n minus 2, and such a sequence is called is called a Prufer sequence. So for a particular tree there is a unique sequence, and for a unique sequence of length n minus 2 on n elements, then we have a unique label tree. So if we are able to establish a one-to-one correspondence between these two, then that says the number of label trees on n vertices will be equal to the number of sequences of length n minus 2 on n elements. Okay, so that's what we are going to do in the proof. Okay, and so let's count the number of such sequences, and we will see that that count will be exactly equal to this thing. Okay, and that justifies this particular correspondence. Okay, and then we will go through an example of how to convert a label tree on n vertices to a sequence of length n minus 2 on n elements and back. If you are given a sequence S on n elements of length n minus 2, how to convert that sequence to a tree. Okay, then after that we will go and prove this statement. Okay, so okay, anyway, let's find how many such sequences will be there. Okay, so how many such sequences of length n minus 2 are there on n elements. Okay, so here we are dealing with a sequence of length n minus 2, so we have to fill n minus 2 positions here. Okay, so we have n minus 2 positions. Okay, and suppose that these n elements are say 1, 2 up to n. Okay, so one possible sequence could be like this. So we fill in 2 here. Okay, we again fill in 2 here. So fill the third position with say 1. Okay, and the fourth position with say 3, and then position with again say 2, etc., etc. Okay, so one such sequence will look something like that. Okay, so here we can see that the first position, it can be filled in n ways. Okay, so this first position, it can be filled in n ways. Okay, so it could be any of these. It could be 1, 2, 3 or up to n. Similarly, okay, so that says the first position can be filled in n ways. Similarly, the second position can also be filled in n ways. Okay, so the first position can be filled in n ways, second position can be filled in n ways. So first and second position can be filled in n into n ways, and similarly the third position can be filled in n ways. Okay, so altogether the first, second and third position can be filled in n into n ways. Similarly, the fourth can also be filled in n ways, okay, and so forth. And the last one, it can be filled in n ways. Okay, so altogether we have okay, this n position can be filled in n into n minus 2 times. Okay, and this multiplication, this product is nothing but n to the n minus 2. So this number corresponds to the number of sequences, total number of sequences of length n minus 2 on n elements. So here we can see that we have the exact kind of quantity here, n to the n minus 2. Okay, so that says, okay, for a unique tree, if you are able to find a sequence, and similarly for a sequence you are able to find a unique tree. Okay, so if you are able to establish a one-to-one correspondence, then the number of labeled trees on n vertices will be equal to the number of sequences as on as number of sequences of length n minus 2 on n elements. Okay, so let's go and see how to convert a tree to a sequence of length n minus 2 and back. If you are given a sequence of length n minus 2 on n elements, how to retrieve back that particular tree. Okay, so we will go through an example, and then after that we will go and prove the statement. Okay, so let's discuss how to convert a labeled tree T on n vertices, okay, to a sequence of length n minus 2 on n elements. Okay, that is how to convert a labeled tree on n vertices to a Prufer sequence. Okay, so let me give the procedure for this conversion, then after that we will work out an example. So the first step is to find a leaf node in this tree T, okay, with the smallest label. Okay, so once you find a leaf node with the smallest label, then we do two things. Okay, first what we do is we will append the neighbor to yes. Okay, and this is how we build this sequence. Okay, a sequence, say yes of length, okay, sequence s of length n minus 2 of n elements. So first you find the leaf in the tree with the smallest level, then append the neighbor of that leaf to s, then after that we delete that leaf. Okay, and okay, after deleting this leaf we get a new tree, and we will do the same kind of thing in that new tree. Okay, again in that new tree we will look for a leaf with the smallest label. Okay, and we will append the neighbor to yes, and we will delete, okay, that leaf, and we continue. Okay, and we continue until we are left with a tree containing 2 vertices. Okay, so repeat until the tree get reduced to a k2. Okay, so we continue until we get this k2. Okay, after removing a particular leaf. Okay, so this is the procedure for converting a label tree on n vertices to a sequence S of length n minus 2 on n elements. Okay, so let's go to an example and see how this can be done. Okay, so let's consider this tree T, and here we can see that the number of vertices is 9. So we are going to convert this tree to a sequence, a Prufer sequence S of length n minus 2. Okay, so the first step is to find a leaf of T with the smallest label. Okay, so here the leaf nodes are 2, 4, 6, 7, 8, and the smallest one is 2. Okay, so let me use a different color here. Okay, so here the smallest one is 2. So once you found this one, we append the neighbor to yes. So initially we start with a null sequence. Okay, so once you find this leaf node with the smallest one, so we append the neighbor is 1, we append that neighbor to the sequence. Okay, then after that we delete this leaf, so we delete this leaf. Okay, so we have this new tree, and what we do is we repeat until the tree gets reduced to a k2. Okay, so again we do the same thing with this new tree. So we look at the leaf nodes. So here the leaf nodes are 4, 6, 7 and 8. So the smallest labeled leaf node is this 4. Okay, so next we are going to consider this one. So we look at the neighbor. Okay, so append the neighbor to yes. So neighbor is 1. So after that we append this 1 to this sequence yes, and we delete 4 from that tree. Okay, so now we have this modified tree, and the leaf nodes are 1, 6, 7 and 8, and here the leaf node with the smallest label is this 1. Okay, so what we do is we look at the neighbor and we append the neighbor of that leaf. So here we are considering this one. This is the one with the smallest label. So we will append the neighbor here 3 to the sequence. Okay, and we delete that leaf node from the tree. So we have this modified tree, and the modified tree the leaf nodes are 3, 6, 7 and 8, and the one with the smallest label is this 3. Okay, and the neighbor is 5. So in the next step we append that neighbor. Okay, here the neighbor of 3 is 5. Okay, so after appending that neighbor we delete this leaf from the tree. So now we have a modified tree, and the leaf nodes are 6, 7 and 8, and the one with the smallest label is 6. Okay, so what we do is we will append the neighbor. Here is 5. So we append the neighbor to the sequence. So after that we get 3, 5, 5, and we delete this 6 from the tree, and we are left with this tree, and the leaf nodes are 7 and 8, and the smallest one is 7. Okay, and the neighbor is 5. So we append the neighbor, which is 5, into this sequence. So after that step the sequence will look something like this. Okay, and we delete 7 from the tree. Okay, and we are left with this tree, and the leaf nodes are 5 and 8, and the smallest one is 5. Okay, and the neighbor of 5 is 9. So we append 9 to this list. 5, 5, 9. Okay, and we delete this 5. Okay, now we can see that after deleting this 5 we are left with k2. Okay, and we stop there, and here this is the sequence that we are looking for. Okay, and here we can see that the length of the sequence is 1 2 3 4 5 6 7. Okay, so here number of vertices is 9. 9 minus 2 equal to 7. Okay, so this is how we convert a label tree into a Prufer sequence. Okay, and here again we can see that if you look into this particular sequence, okay, no leaf nodes will appear in this sequence. That's one observation. Okay, and another observation is that here some of the nodes get repeated. For example, one get repeated twice here, right? So that corresponds to the degree of that node minus 1. Okay, so here the degree of this node is 3. Okay, so here we can see that if we look into the sequence, that one get repeated twice. So that corresponds to number of times a particular node get repeated here is the degree minus 1. Okay, and because of reason the leaf node will not appear in this one. Similarly, you can see that 5 is repeated 3 times here. So the degree of 5 is 4. So that says 4 will get repeated 3 times in this sequence. Similarly, if you look at 9, the degree of 9 is 2. Okay, so that says 9 will only repeat once. Okay, and similarly with 3, the degree of 3 is 2. Okay, 2 minus 1 is 1. So we can see that 3 is repeated only once here. Okay, and again we can see that okay, the sequence length is only n minus 2. Okay, in this case 7. So you might ask why the sequence length has to be n minus 2. Okay, so let's go and answer that question. So this question, why this sequence has length n minus 2. Okay, so as I said, if you look into that sequence, we have this observation. We can see that no leaf okay gets appended to S. Okay, so you can see that from this sequence, right? Okay, so 4 is not appeared here. Okay, 2, 6, 7 and 8. Okay, so those leaf nodes are not appended to this sequence. Okay, and again we can see that some things get appended more than once. For example, here we can see that this one is get appended twice, 5 is get appended twice, and we can see that every vertex v is added to this sequence a total of degree minus v. Okay, degree minus that particular vertex. So 5 is added to this sequence 3 times, right? And the 3 corresponds to degree of 5 minus 1, and we can see that 1 is added twice and degree of 1 is 3. Similarly, 9 is added 1, degree of 9 is 2, and 3 is added once, degree of 3 is 2. Okay, so some things get appended more than once. Okay, so here again we can see that every vertex v is added to S a total of degree of that vertex in that tree minus 1 times. Okay, so we saw that here, right? 5 degree is 4. Okay, 1 okay degree is 3 and so forth. Okay, and let's see why S has length n minus 2. Okay, we are going to use these two observations to come up with why always this S has length n minus 2. Okay, so we are dealing with a tree with n vertices, okay, and say m edges, and since okay we are dealing with a tree, m is equal to n minus 1. Okay, so let's count the number of terms in our sequence. Yes, okay, so by that observation, that is equal to the number of times the vertex in T is added, right? Okay, how many times the vertex 1 is added, the vertex 2 is added, vertex 3 is added, something like that. Okay, it is going to be the number of times the vertex V is added to this S, and we observed that number of times a particular vertex is added is exactly equal to the degree of that that vertex V in T minus 1 times. Okay, so if you sum this, you get this will be equal to sum of every vertex in the vertex set of T, degree of that vertex in that graph, minus sigma E of T 1 times. Okay, that is equal to, so here what we are doing is we are summing up the degree of each vertex in that graph. Okay, so that is nothing but 2 times the number of edges using the handshaking lemma, and here we are summing this one n times, so that corresponds to n here. And since we are dealing with a tree, m is nothing but 2n, m is nothing but n minus 1, so this is 2n minus 1 minus n. Okay, so if you do the algebra, you get 2n minus 1 minus 2n minus 2 minus n, which is equal to n minus 2. Okay, and here what we are counting is the number of terms in S. Okay, here we saw that the number of terms in S is n minus 2, and this is why this S has length n minus 2. Okay, so we will continue with this conversion in the next video. So in the next video we will show how to convert a sequence S of length n minus 2 on n elements to a label tree. Okay, then after that we will go and prove this statement. Okay.